Okay, everybody, we are on our last portion for section 7.1, and this marks about a third of our module for the week. So here we're going to be computing a sample size to estimate a population mean, and here we're typically going to be given our margin of error boundaries and what confidence level we want to do. Okay, the derivation here is outside of the scope of the course, but it's nice to see how this equation that we see on our formula book came to be. Basically, we're using the maximum margin error equation that we worked with in the previous example and the previous videos. And we basically manipulate it to solve for our sample mean, okay? So same equation, just a manipulation. And we end up with this equation that is bolded on the bottom after all of that manipulation, where we solve for n. So because that was a super quick explanation, let's go on to the example as well. So a hospital wants to start a new study to estimate the average systolic blood pressure population mean in the adult patients. And for the past studies, we know that the population standard deviation of the systolic blood pressure is 15 millimeters of mercury. How large of the sample should be taken to be 99% confident that the sample mean is within 0.2 of the true mean systolic blood pressure population mean? So let's see. First, let's write the equation so that we're not too lost. We have the sample mean is equivalent to our critical value multiplied by our population standard deviation over our margin of error all squared, okay? So that means we're going to do this fraction calculation first, and then we're going to square everything at the end, okay? So let's write out all of the variables that we need. So we need our critical value. Here it's going to be 99. And we don't know what that is. The other previous examples that we did was a 90% confidence level and a 95% confidence level. So we're going to have to do that first step again as well. Our population standard deviation here was given to us as 15 millimeters of mercury. Okay. And our margin of error is given to us as well because they want us to find a sample mean within 0.2 of the true mean systolic blood pressure. So this 0.2 or 0.2 is going to be our margin of error, okay? That's actually a pretty narrow margin of error. So it may affect our sample size greatly. So before we find our sample size though, we're going to have to find our critical value. So when we're finding our critical value, we're going to want to draw it out. So I'm going to take this right-hand side to find the critical value. First step is always to draw it out. And we really don't have a lot of space for our tails here. So I'm going to draw them super close to the edge of our drawings. You guys are experts at this point. Our confidence level is the area in between. So that means that the area at the tails is the complement, which we know as 0.01. If we're only finding the left boundary because our table is usually given to the left-sided boundaries, we're going to have to divide that area by 2 because we're not considering the area at the right tail, and that'll give us 0.005. Okay, so the probability that z is going to be less than negative z 0.99 is going to be 0.05. 0.005. My bad. To find that that negative critical value, we're going to have to look at our chart for where we can find 5 thousandths. So let's see if we can find that on this chart here. Yes, we can. So because this is an old chart, I'm going to erase all of this so we don't get too confused. And we're going to look for 5 thousandths. So it's going to be 0.005. The closest values that we have here are going to be 0.051 and 0.0049. So we're going to take the midpoint of those. Those two values are negative 2.57 and negative 2.58. Okay. So we can do the addition and divide, but we're going to end up with that as our value. Okay, now that we have our critical value, which is actually going to be the positive of this, we can now find our minimum sample size needed. So just for completeness, I'm going to write it, the number that we just found out here in our little list of variables. And now we can solve for the sample mean. That is going to be equivalent to 2.575 multiplied by our population standard deviation of 15 divided by our margin of error of 0.2. Plugging this value into our calculator, let's do the numerator first. We have 2.575 multiplied by 15. This number is going to be 38.625, and that number is going to be divided by 0.2. This value that we have in parentheses is actually going to be 193.125, and we're going to have to square it to find our final value for the margin of error. That number is going to be 37,297.27. Okay. I would be very concerned if we had 27ths of a person, 2700ths of a person, and we cannot leave our answer like this. So anytime we have a sample size, we're going to be rounding our value. Specifically, we're always going to round up. Okay? Even if this number in our tenths place is telling us to round down. Okay? Always round up. Because we're finding the minimum value for our sample size. So technically, with the number that we calculated, it's going to be greater than 37,297 because even by a fraction, we're greater than that number. So to be assured that we can get the margin of error that we're looking for, we're trying to find an even better margin of error at this point, basically. So we want to round up, okay? You're always going to round up if you have a decimal. Now, if you get a whole number, keep it as it is. But whenever you come across a decimal, round it up. So your sample size here is going to be 37,298. That is a lot of people. So, and a lot of money to do this study. So if you're up for it and you can do it, a lot of researchers might decrease their margin of error, or increase their margin of error, I should say, so that they can have a smaller sample to pick from. All right, and that concludes 7.1.